Hi, this is Ms. Warnell, and this is our new unit on stoichiometry. Be sure to have out paper and writing utensils as well as your calculator. So for stoichiometry, our objectives, we will be finding the mole, mass, and particle relationships between and among reactants and products in a reaction. We're also going to be calculating the limiting reactant and the percent yield. We will also find the mass and volume relationships between reactants and products with gases. So what is stoichiometry? So stoichiometry is the calculation of quantities in a chemical reaction. So in previous units we have balanced chemical reactions. Now we're going to begin using our balanced reactions to come up with numeric values for the quantities of reactants and products that we may be producing. So anytime you have some reactants, they will react to give you some products. As well as products, you may have one of the reactants a little bit left over, and we'll talk about that a little bit later on in the unit. So understand the law of conservation of mass, but what does that mean when we look at chemical reactions? So we've been balancing chemical reactions, and you know the number of atoms on the reactant side should be equivalent to the number of atoms on the product side. So when we begin stoichiometry, this unit, we need to always start with a balanced chemical reaction. So in a balanced reaction, some things are equal or conserved and some are not. So let's take a moment and look at that. All right, so we have an equation here. This is a decomposition equation of water into hydrogen and oxygen. Take a moment here to note that the hydrogen and the oxygen has a subscript of 2. Please do not forget your 7 diatomic elements here. Being hydrogen, oxygen, nitrogen, chlorine, bromine, iodine, and fluorine. All right, so we need to balance this. We have 2 oxygens on the product side, so we'll put a 2 here to make you have 2 oxygens on the reactant side. Now we have 4 atoms of hydrogen on the left, so let's put a 2 here to make there be 4 on the right. All right, so in terms of atoms, we could look at this and we could say we have how many atoms of hydrogen? We have 4. And then we have 2 atoms of oxygen. Looking at the product side, we have 4 atoms of hydrogen, and we have 2 atoms of oxygen. So the 4 and the 2 is 6, and the 4 and the 2 is 6, so we have the same number on both sides, so yes, it is conserved. Looking at mass, you know the molar mass of water is 18.02. You have 2 molecules of water, so 2 times 18.02 is 36.04. Looking at hydrogen, hydrogen's molar mass is 2.02 times 2 that you have 2 molecules of it, so we get 4.04, and then we have 2 atoms of oxygen, and each one is 16, so it's 32. If we add this 32 and the 4.04, we do get 36.04. So the mass is conserved. Looking at moles. Moles comes from these coefficients. So we have 2 moles of water, gives us 2 moles of hydrogen, and 1 here, understood 1 mole of oxygen. So for the reactant side, we have a total of 2 moles. For the product, we have 2 moles of the hydrogen and 1 mole of the oxygen. 2 and 1 is 3. Does not equal 2. So it is not conserved. For representative particles, we're dealing with 6.02 times 10 to the 23rd. We have 2 moles on the reactant side, so we have 2 times 6.02 times 10 to the 23rd. On the product side, we have 2 moles of hydrogen, so 2 times 6.02 times 10 to the 23rd. And then we have 1 mole of oxygen, 1 times 6.02 times 10 to the 23rd. I haven't done this math, but I do know this side added together does not equal that side. And so, no, it's not conserved. So the number of atoms and mass are always conserved because of the law of conservation of mass. But moles and molecules are not necessarily conserved because they apply to each compound into the coefficients and not each element. So how to solve equations or, questions about the numbers in chemical reactions? Well, we're going to have to do some mole conversions, which you already know how to do. You're going to need to convert between units using dimensional analysis. You already know how to do. You're going to need a balanced equation that you already know how to do. You already know how to pick the given from a problem. You already know how to do that. And convert to moles and use the mole ratio. That's what's going to be new. So where are we going to get the mole ratio? Well, the mole ratio comes from a balanced equation. It is the coefficients. You're going to be looking at the coefficients to get the mole ratio. Right? And then mole ratios are your new conversion factors. Mole ratios for the decomposition of water. So here you have an equation here. So if you want to do the mole ratio between water and hydrogen, you go to water in the problem. And what's the coefficient in front of water? It's 2. So you put a 2 there. What's the coefficient in front of hydrogen? 2. So that's the mole ratio between water and hydrogen. It's a 2-to-2 ratio. Or what's the mole ratio between water and oxygen? You go to water, there's a 2 in front of it. You go to oxygen, there's a 1. It's a 2-to-1 ratio. Between oxygen and hydrogen, you go to look at your balance coefficient, balance reaction for your coefficient. You get a 1 in front of oxygen, and you get a 2 in front of hydrogen. And we can vary that up a little bit. Oh, yay! What about between hydrogen and water? What's in front of hydrogen? 2. What's in front of water? A 2. What about between oxygen and water? Well, what's in front of oxygen? 1. What's in front of water? 2. What about between hydrogen and oxygen? Well, what's the coefficient in front of hydrogen? 2. What's in front of oxygen? 1. So those would be your mole ratios. So let's work the problem. How many moles of hydrogen gas are in 5.3 moles of water? This is different from previous problems. In previous problems, we always had the same substance. Now we have a different substance. So we always start by making sure we have a balanced equation. That's the most important part of stoichiometry. You begin with the balanced equation. So now we're going to start by writing down our given after we balance our equation. We have 5 moles of water. Notice that I'm writing the unit and the substance. And whatever unit's up top, we're going to put down on bottom, just like we've always done. And instead of going from moles of water, we want to go from moles of water to moles of hydrogen. So we're going to go to moles of hydrogen. And then this is that mole ratio. Where do we get our mole ratio from? The balanced equation. So what's in front of hydrogen? A 2. What's in front of water? A 2. And notice that I've written down the substance and the unit each time. You are required to do that. And then when we multiply 5.3 times 2 and then divide that by 2, we get 5.3 oh goodness, moles of hydrogen. A little bit happy here with the scratching off. We didn't scratch that off. I'm going to fix this. Sorry. There you go. Alright, notice that I wrote the substance in the unit, substance unit, substance unit. Vice versa. The substance unit, the unit substance, the unit substance. And so we have 5.3 moles of hydrogen, and I did pay attention to sniff the creaky tip. Right, for the next one, how many moles of water are needed to form 1.7 moles of oxygen gas? Oh, we already have a balanced equation. Once again, that's the most important step, is make sure you have that balanced equation. All right, so then we're going to write down the given, 1.7 moles of oxygen gas. And whatever unit's up top comes down on bottom. And then moles of oxygen gas, we're trying to get to moles of water, so we'll go to moles of water. And where do we find our mole ratio? From the balanced equation. A 2 is in front of water, and a 1 is in front of oxygen. We cross that out. Notice I wrote the unit and the substance, the unit and the substance, the unit and the substance. So when we multiply 1.7 times 2, then divide that by 1, we should get 3.4. I am paying attention to significant digits, and I am showing all of my work. This concludes video 1 of stoichiometry. You should have taken high quality and in-depth notes with examples, rewatch the videos needed, and ask any questions.